Oh, attendance. Akila Coleman? No. Akila Coleman? No. Robinson Hale? Ricardo Pinto? Kira Fry? Ephraim Reboot? Ephraim? Oh, Ephraim? Ephraim Reboot? No, okay. Ali Sims? Domenica Soles? Tersan Strong? Aaron Swain? Gina Trombetta? And Darana Woodson. Okay, just making sure the number of people are marked in is equal to the number of people who are here. So let's get started. I'm Dr. Michael Keiderling. I teach physics here. Oops. Best way to get in contact with me in general is my email, which is mkeiderling@ccsj.edu. My office is room 335, which is, if you continue down the hall here, right around the corner, or left around the corner, is my office. First room, once you go around the corner. I'm around here, this hallway, pretty much all Monday through Wednesdays. On Mondays and Wednesdays. I will not be on campus Tuesdays and Thursdays. I teach at another school on those days. So you should email. Lecture for this class will be 4 to 5:15 p.m. Lab is scheduled from 5:30 to 6:45 on Wednesdays. It will generally be shorter. We will start immediately after we finish lecture. So we'll include that 15-minute break in so we can get done with the lab sooner. Because I don't want you guys stuck here till 6:45. My office hours are officially from 10 to 11:30 on Monday and Wednesdays. But I'll generally be around Mondays and Wednesdays. So if you come during the lunch hour, I won't be officially in my office hours, but I'll probably be around here. Name? So you're gonna need a calculator for this class. Scientific calculator. We're doing, this is physics class, there's gonna be math. You'll need a scientific calculator with these functions. You can use a graphing calculator if you have one and you want to use it. It's not a problem. You cannot use the calculator function of your phone or a portable computing device on exams. I do have calculators I can loan out for exams, but it's good to have your own. The questions from the exams. The exams are written by me. I'm making up questions, but they're based on the content we covered in lecture and in the book in the appropriate sections. So you need to show up to class and keep up with the material. You can work with each other to work on homework. The homework will be online through Mastering from Pearson. I will demonstrate how that works. I don't have a problem with you working together on homework and things like that. Or you're going to work together with each other on labs. Just on tests, you need to work on your own. For the tests, the way I do tests, I allow you one sheet of notes to use as a formula sheet. So you can write your own formula sheet. You get 1 page of paper. You can use both sides of notes for a formula sheet. I do accept late work. For the homework online, it's set up with an automatic penalty. You can just keep working. It'll automatically penalize you. I will go on and make sure that's set up correctly. But it should it will generally max out at about 10 to 15%. I think the way it's set up for this class is that the penalty gets bigger the more you're late. But there's a cap. But I'll accept late work. You can always turn in work late. If you're not going to be able to make the class, let me know in advance. Name? I don't need a doctor's note or anything like that. I just need you to send me an email in advance. Let me know. If you need to reschedule a test, let me know well enough in advance and we can work something out. I know people are in sports and stuff, and they got to work around it. And if you missed the class for whatever reason, all the lectures are being recorded and will be posted to Blackboard. So I'll be posting all the lectures to Blackboard. All the slides are already up there. In the lectures section, there's a folder called Slides. I will also be posting recordings in that section. That's why I'm using the. So let me show you how you'll get to your homework. So from the student view, homework, it will be here in the homework ebook. Your textbook is an ebook because they apparently ran out of physical copies. But so here's a link to the e-text, which will take you to the textbook. And here is the link to the course home for mastering. And each individual assignment is linked in this folder. So you'll go through here. You may have to put in a link in a code from your eCampus to access this the first time. If you're having any trouble accessing mastering, please talk with me. I'll sit down with you and help you work it out. I can't remember if we have I don't remember if we have it just run through Blackboard or not. Oh God, this is doing weird things because I went in as a fake student. Exit the preview, delete this person. But once you go into mastering, you'll see something like this. This is a little different, but you'll see the new assignments listed here and when they're due. So your first assignment is the Introduction to Mastering Physics, and it is due on the 4th. And you can see, I would pretend to be a student, but somehow this did something weird. And if you have any questions about the homework, just let me know. This is our schedule. For the first couple of weeks, we'll start with an introduction to physics, and we'll go on to talk about motion, one-dimensional motion, which is chapters 1 and 2 in your book. Then we'll move on to vectors and motion in 2 dimensions. That's chapters 3 and 4. And then we'll do, which might bleed a bit into week 4, especially with the new shorter class periods. And then we'll do forces and Newton's laws of motion. That's chapter 5. And applying Newton's laws, that's chapter 6. And then we'll have an exam on chapters 1 through 6. That's the current plan. And then we'll cover working kinetic energy, chapter 7, potential energy and conservation of momentum, and linear momentum, conservation of energy, and then linear momentum, and have an exam on those. And then lastly, we'll talk about rotational momentum, rotational dynamics, and oscillation about equilibrium, and have an exam on that. The schedule is, that should hopefully be what we manage. The new class length may cause things to slip a little. We'll figure it out. Your lecture, roughly 2/3 of your grade is the tests, and roughly 1/3 is your homework. And the lab is technically a separate class. There are going to be about 8 labs. Each lab is, copied that from another class. Each lab is 10 points each, and they're all equally weighted. We do all the labs. Any questions about any of that? If you're having any issues with Pearson and getting on, just let me know and I'll help you. I don't remember exactly how it's set up for Pearson. I think it's just you have to log in through Blackboard and you don't have to enter a code, but you might have to enter a code. I can't recall which publishers we have the automatic system with and which ones we have to enter codes. If you check on eCampus, you'll see if you have a code. Or it'll ask for a code, and then if you need a code, you need to go to your eCampus site, and there'll be a code that you can access. And if you're having any trouble with it, just see me. I can walk you through it. Just drop by in the morning during my office hours or sometime. If you have questions after class, I can help you through it. Access code will be so your course materials in the bookstore. It's not something you can access directly on, well, maybe. Okay, so that doesn't work, but you may be able to go log into Thanks for logging directly. Yeah, sorry, this is always confusing, but once you get through it, it'll work. Yeah, so you need an access code. You can get the this is sort of the instructions. Go to ccsj.ecampus.com, log into your account there. And on your digital bookshelf, there will be a access code that you can use for login. You may have to open it through VitalSource or something, but that should work. So let's start with an introduction to physics. So we'll talk about physics and the laws of nature, the units we're going to use, the units of length, mass, and time, which are the units you need for all of describing motion and dynamics. Everything builds off of that. We'll talk about the idea of dimensional analysis, significant figures, scientific notation and round-off error, how to convert units, the idea of order of magnitude calculations for doing quick approximations, scalars and vectors, what a scalar is, what a vector is, and just sort of the general problem-solving process you can use in physics. So physics is the study of the fundamental laws of nature. And these laws can be expressed as mathematical equations, and quite a bit of complexity can arise from relatively simple laws. So, you can write fairly straightforward, simple equations and get quite complicated things. We will be using the metric system. The SI units are for length, mass, and time. The units, oh, this is updated. For length was defined originally. So the metric system tries to define units based on physical quantities. Length was originally defined as 1/10,000,000th of the distance from the North Pole to the equator. Now it is the distance traveled by light in 299,792,458 of a second, exactly. We set the speed of light to an exact value, a whole number, and use that. We measure the speed of light very accurately based on our previous definition of the meter, and then define the meter based on a very accurate value of the speed of light. And for mass, actually up until 2019, this is out of date because this book was published. This edition of the book came out before 2019. 1 kilogram was the mass of a particular platinum iridium cylinder kept in the International Bureau of Weights and Standards in France. This is not the case anymore. Mass is defined based on much like length is defined based on the speed of light, mass is defined based on Planck's constant, which is another universal constant. It has to do with a whole bunch of stuff. Originally, it had to do with what's the energy of light based on its frequency. But again, it had to do with a whole bunch of stuff. But it's based on Planck's constant. Time is the second. The second was originally a fraction of a day, 24 hours, 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute. That comes from ancient Babylonian math, which originally is why we have base 60 stuff all over the place. Because those divisions were originally used for angles. There are minutes and seconds of angle. And then they were also applied to hours for time. 1 second is the time for radiation from a cesium-133 atom to complete 9,192,631,770 oscillations in the hyperfine transition. It's a specific transition for cesium-133 atoms. because every cesium-133 atom in the universe is identical, this oscillation will be the same for every cesium-133 atom. So you can count these oscillations to define a second. There is some work being done, possibly changing the definition of a second to a faster oscillation, so we can measure even dinkier amounts of time. But that hasn't occurred yet. So it is still defined based on the cesium-133 atom. But yeah, there's some people working on making clocks that are based. That's what an atomic clock does. It vibrates cesium-133. And here are some example distances. So we have very big things like the distance from Earth to the nearest large galaxy is around 2 times 10 to the 22 meters. So 2 followed by 22 zeros. The diameter of our galaxy is about 1 times 10 to the 21 meters. The distance from Earth to the nearest star is about 4 times 10 to the 16 meters. A light year, the distance light travels in a year, is 9.46 times 10 to the 15 meters. The average radius of Pluto's orbit is around 6 times 10 to the 12 meters. The distance from the Earth to the Sun is about 1.5 times 10 to the 11 meters. The radius of the Earth is only 6.37 times 10 to the 6, 6.37 million meters. The length of a football field is about 100 meters. The height of a person is around 2 meters. The diameter of a CD is around 0.12 meters. The diameter of an aorta is 0.018 meters. The period on a sentence is about 5 times 10 to the minus 4 meters. Diameter of red blood cells, like 8 times 10 to the minus 6 meters. Hydrogen atom is around 10 to the minus 10 meters. And a proton is around 10 to the 2 times 10 to the minus 15 meters. There's a big difference between the size of an atom and the size of a proton. There's a lot of empty space in the middle of that. Some masses. An electron is 9 times 10 to the minus 31 kilograms. A hydrogen atom is about 1.61 times 10 to the minus 27 kilograms. The bacterium is about 10 to the minus 15 kilograms. A red blood cell is about 10 to the minus 13 kilograms. A honeybee is around 1.5 times 10 to the minus 4 kilograms. A baseball is around 0.15 kilograms. A human is 70-ish kilograms. A car is around 1,200 kilograms. An elephant is about 5,400 kilograms. The space shuttle was about 2 times 10 to the 6 kilograms, or 2 million kilograms. The Earth is about 5.97 times 10 to the 24 kilograms. The Sun is about 2 times 10 to the 30 kilograms. And the Milky Way galaxy is about 4 times 10 to the 41 kilograms. And sometimes, the age of the universe is around 4 times 10 to the 17 seconds. That's about 13, 14 billion years. The age of the Earth is 1.4 times 10 to the 17 seconds. The human species has been around for only about 6 times 10 to the 12 seconds. Human lifetime is 2 times 10 to the 9 seconds. A year is 3 times 10 to the 7 seconds. A day is 8.6 times 10 to the 4 seconds. The time between heartbeats is around 0.8 seconds. Human reaction time is around 0.1 seconds. One cycle of a high-pitched sound wave is about 5 times 10 to the minus 5 seconds. One cycle of an AM radio wave is about 10 to the minus 6 seconds. And one cycle of a visible light wave is around 2 times 10 to the minus 15 seconds. Now, we use a number of abbreviations for a metric system to represent very big and very small numbers. So if there's no prefix, it's just the unit. If we go up for bigger, if we have 10 of the unit, it is deca. So a decameter would be 10 meters. 100 is hecto. A hectometer is 100 meters. These don't get used very often. Kilo is 1,000. A kilometer is 1,000 meters. A kilogram is 1,000 grams. Mega is a million. Megabyte, megameter, megaton. You may have heard these. These are all a million. Giga is a billion, 10 to the 9. Tera is a trillion, 10 to the 12. Peta is 10 to the 15. It's 1,000 trillion. And then we're going small. We have deci, that's a tenth. Centi, that's 100th. Milli, that's 1,000. Micro, that's a million, 10 to the minus 6. Nano, that's a billionth, 10 to the minus 9. Pico, 10 to the minus 12. And femto, 10 to the minus 15. Generally, the stuff in the middle minus these two is what you're going to run into. Generally, people don't deal with pico or femto units. They're just too small. But you do get micro and nano sometimes. And things like mega, giga, tera, peta, they show up in computing more than anywhere else. But these are standard prefixes that can be applied to any unit. So it's that sort of universal system. So given if you have a softball that has a diameter of 375 millimeters, how would you convert this to meters and to kilometers? And if a house sells for $550,000, what is this in megadollars and kilodollars? So just to make sure I will work these out for you to see. I'll go through the conversion process. So if a softball has a diameter of 300 and we have 375 millimeters. If we want to convert this to meters, well, we know 1 millimeter is 10 to the minus 3 meters. So we can multiply by the same value. This is multiplying by 1. Now let's multiply by 1. So 375 times 10 to the minus 3. The millimeters cancel. We're left with meters. This gives us 0.375 meters. And if we want to continue on to kilometers, 10 to the third meters is 1 kilometer. So this ends up being 3.75 times 10 to the minus 4 kilometers, or 0.0000375. For tests on homework and stuff, well, for tests at least, I'll accept either. The homework will probably accept either, but you may have to enter in scientific notation in a weird way, because online system. I think it's with an E. Now, if you have a house that sells for $550,000, what is that in megadollars and kilodollars? Well, we have 550,000 dollars. 1 megadollar is 10 to the 6 dollars. So this comes out to 0.55 megadollars. And if we do the same thing with kilodollars, 1 kilodollar is 10⁶ dollars. Sorry, that's 10⁻³ dollars. So this is 550 kilodollars. Any questions? You okay with me erasing this? So here, we want to convert 250 megameters to meters. Megameters, we will multiply by 1. So we have 10⁶ meters is 1 megameter, and this will be 2.5. So it's 10⁻⁴. Oh wait, no, that's wrong. I did that wrong in my head. It'll be 250 or 2.50 or 2.5 times 10⁸. Units. And if you want to convert 3 kilograms to milligrams, that's something you might actually have to do. This, what you can do, you can either know the conversion between kilograms and milligrams, but you can convert from kilograms to grams and then from grams to milligrams, just based off their prefixes. So 1 kilogram to the 3rd grams, and then 1 milligram is 10⁻³ grams. So we'll take 3, we'll multiply by 10⁻³ and divide by 10⁻³, and we'll get 3.0 times 10⁶ milligrams, or 3 million milligrams. Now, one of the things that's very useful for checking what's going on is dimensional analysis. So any valid physical formula has to be dimensionally consistent. Every term that's separated by a plus or a minus or an equal sign has to have the same dimensions. You can't add 2 things, you can't add seconds and meters. How do you add 30 seconds to 5 feet? For example, I mean, you can, it is in fact possible to do that, but you have to start doing some weird things to do with special relativity, which we're not going to get into. But any valid physical formula should be dimensionally consistent. Each term should have the same dimensions. So for example, So velocity is length over time. And that means, and distance is length. So distance should be velocity times time, so the times cancel. And it turns out this dimensional analysis is really powerful. Another thing, velocity is equal to acceleration times time. You can see acceleration is length over time squared. You multiply acceleration by time, one of those times goes away, and we're left with the units for velocity. Another one is energy is mass times velocity squared, E equals mc squared. Well, energy is mass times length squared over time squared. And that is velocity squared. I mean, energy is also mass times velocity squared in another equation up to a constant. And dimensional analysis is such a powerful technique, combined with some basic estimations. It got someone almost arrested for espionage. There was a British physicist who was able to correctly figure out the power of an atomic bomb using dimensional analysis and a single picture of the explosion. And he was accurate enough that he got investigated to see if he was actually spying on US military secrets. So here, for example, this is an equation we will learn in a later chapter. Show that, so all the x's are position, they are distances. Velocities are, well, v is velocity, it's a velocity. T is time, acceleration is acceleration. So as a quick reference, x is length, velocity is length over time, and acceleration is length over time squared. So if you wanted to go through and work out the dimensions for everything, well, we have x is length. We have an equal sign. We want to check that everything that's separated by an equals or a plus is the same dimensions. X0, well, that is also length. That's just another distance. We have a plus. We have velocity, v0 times time. So we have length over time. Capital T times a capital T. And then we have 1/2 acceleration times time squared. 1/2 is just a constant, we ignore it. Acceleration is length over time squared. And then we have time squared. So this is time squared. So this is length. This is length. Length times time. Time cancels. Length over time times time, the time cancels. This is length. And length over time squared times time squared. The times also cancel. This is also length. That's the way you'd formally do it with these length, distance, time symbols. The way I usually do it, that I find is a little more intuitive and faster, is I just use the units. So that would be for x, we have meters, meters per second times seconds, meters per second squared times seconds squared. And that's just a little easier to think about. Now, this isn't always perfect because sometimes we use weird units for things, but Generally, the units are a little easier to do intuitively. Any questions about this? It's just a tool to check that you're using the right frickin' formula. Somewhere I have a poster or a t-shirt that says "Don't drink and drive," and there's a whole bunch of equations, but they're all wrong dimensionally. Okay. So that's just, if you put together a formula for something, that's a good way to check your work, that you're not doing something weirdly wrong. Now, the accuracy of measurements is limited. And significant figures are the number of digits in a quantity that are known with certainty. So the number of significant figures after multiplication and division should be the number of significant figures of the least known quantity. In this class, I'm not going to be super picky about significant figures on tests because it means I can use nicer numbers on the tests. But just in general, if you're reporting something, the general rule of thumb that will keep you safe, look at the stuff you started with. Your answer should have the same number of significant figures as the input that had the least number of significant figures. I'm not going to be super picky about that in this class, especially because I don't think all the problems on the homework and things are consistent about that. So, and then it lets me on tests use nice round numbers to make your calculations a little easier. But just in general, an answer should not have, you should not start with like things with only a couple significant figures and give out like 20 digits. But yeah, I'm not going to be super picky. So an example, if a tortoise travels at 2.51 centimeters per second for 12.27 seconds, how far does the tortoise go? If you plug that into your calculator, that'll give you probably 7 or so significant figures, something like that. 2.51 times 12.27. Yeah, it gives you 6 significant figures in your output. But you don't actually know anything to that accuracy. So you'd have to round it off to 30.8 centimeters, which is the 3 significant figures of this. So that's the important idea. But yeah, I won't be super picky in this class. We will be doing things with scientific notation. Leading zeros and trailing zeros can make it difficult to determine the number of significant figures. The scientific notation makes it easier to write this out. Each of these has 2 significant figures. We write these as a number from 1 to 10 multiplied by a power of 10. And that makes the number of significant figures much clearer, and it's great for really big numbers and really small numbers. If I don't specifically ask for something in scientific notation, you don't have to give an answer in scientific notation. If you give an answer in scientific notation, that is fine. So here are some examples. And the last digit in a calculated number may vary depending on how it's calculated due to the rounding off of insignificant big digits. The general rule of thumb, keep at least a few extra digits beyond the right number of significant figures until the end of the calculation and round them, or just round at the end. So for example, 2.21 with 8% tax rounds to 2.39. 1.35 with 8% tax rounds to 1.46. If we add those up, we get 3.85. But if we add them together and then do the tax afterwards, we get 3.84. That's a rounding issue. Because we rounded in the middle, before we added, we ended up with a slightly different answer. So general rule of thumb, round at the end. The online homework deals with this. There's a certain percentage of error you're allowed in your answers. I have to look what it's set, but it's like 1 or 2%. That should deal with any sort of round off error like that. So here are some quick problems about significant figures. 35.2 meters divided by 5.0 seconds. You will get 7.04 meters per second on your calculator, but 5.0 only has 2 significant figures. So this would be correctly rounded as 7.0 meters per second. Here we have 15.56 meters times 6 meters. So this will give you 93.36 meters squared. But 6 meters only has 1 significant figure, so this will be rounded to 90 meters squared. 125 meters divided by 5 meters gives you 25 meters. Just 25, sorry. The units are gone. And this would be rounded to 30 because this has 1 significant figure. Now we have 25 meters times 25.0 meters times 5.00 meters. That's 125 meters squared. And you don't need to do anything to that, but that is 3 significant figures. And these are all 3 significant. You okay with me erasing this? Okay. Now, sometimes you'll need to convert from units between systems, like feet to meters, or things like that, or pounds to kilograms or something like that. It will not happen on any of the tests. All the tests will be in metric. But at least I think they are. Yeah. There might be some in the homework. So for example, this is the same process. 1 meter is 3.281 feet. So 1 is 1 meter over 3.281 feet. So 316 feet times 1 meter divided by 3.281 feet gives you 96.3 meters. You need to set up a fraction so the units cancel properly. The goal is to make feet cancel. You can do a whole bunch of that in chemistry. So 1 inch is 2.54 centimeters. So how many centimeters is 12 inches? And how many inches is 10 centimeters? So 12.0 inches. 1 inch is 2.54 centimeters. So 1 is equal to 1 inch over 2.54 centimeters, and also equal to 2.54 centimeters over 1 inch. So 12 inches is 2.54 times 2.54 centimeters over 1 inch. Gives us 30.48 centimeters, which we will round to 30.5 centimeters, because 12.0 is 3 significant figures. And then how many inches is 10 centimeters? 10 centimeters, 1 inch over 2.54 centimeters. This will give us 3.93700774 inches, which will obviously round to 3 significant figures, which is 3.94 inches. So you got that? So let's talk about order of magnitude calculations. Order of magnitude calculations are a way to do estimates. And estimates are useful as a sort of rough check for your detailed calculation. And if your answer is very different from your estimate that you made, you did something wrong. And you can also use order of magnitude calculations to estimate numbers where a precise calculation can't really be done. And so a lot of the times you can get something to the nearest order of magnitude that's like, are we talking 100 or are we talking 10? Or are we talking 1,000? Those are orders of magnitude. What power of 10 are we doing? And we can use this to estimate numbers where a precise calculation can't be done. And so you can sort of go through and do a sort of quick estimation to get a rough idea of where things should be. When we deal with values that we observe or look at, we have 2 types of values. We have scalars and vectors. Scalars are quantities that just have a value, like mass is a scalar. Temperature is a scalar. Height is a scalar. They can be positive or negative. Speed. Yes. Vectors are quantities that have both a magnitude and a direction. So distance is a scalar. Displacement is both how far and how far away, how far and in what direction I am from the origin. You know, that would be something like 10 feet north. That is a vector. Force is a vector. Velocity as opposed to speed is a vector. Magnetic field is a vector. So things that have a direction are vectors. And so there's no perfect solution that always works for solving problems in physics, but here are some guidelines. Read the problem carefully. That's the most important thing. Read the problem. Maybe note down what is given in the problem, so what you know, and what you're actually being asked to find. Drawing a picture is extremely helpful. So a sketch of the system is extremely helpful. Then you want to visualize what the physical process is, make a plan, and identify the appropriate equations. If you know what you're looking for and what you're given, you can often use that to figure out what the right equations are. Because what you're looking for has to be in one of the equations you're using, and what you're given has to be in the equation you're using. Sometimes there'll be an intermediate step, but you can often figure that out by thinking about the process and what equations you're dealing with. Then you can solve the equations, check your answer makes sense, and maybe explore limits in special cases. Do the extreme values sort of make sense? Does this make sense? So, summary of chapter 1. Physics is based on a small number of laws and principles. The units of length are meters. The units of mass are kilograms. The units of time are seconds. All items in an equation must have the same dimensions, which often means that you can figure out what the right equation for something is by grabbing things that would make that dimension, roughly. The result of the calculation should only have as many significant figures as the least accurate measurement used in it. You can convert from one unit to another by multiplying their ratio. Order of magnitude calculations are designed to be accurate within a power of 10. Scalars are numbers. Vectors have both a magnitude and a direction. And sort of the problem-solving technique is read, sketch, visualize, strategize, identify equations, solve, check, and explore limits. And this is all in your book in chapter 1. Yeah, I went a little quick on that because I was a little worried about the new shorter class times, but I finished a little early. Well, we'll see how it goes for the rest of the semester. I think I'm just going to finish there because that's a nice ending point. If you have any questions or if you want a hand with trying to get in to your homework, I will happily do that.